On your first day, accessing a university supercomputer, the system administrator gives you one strict rule. Do not run heavy computations on the login node. Most beginners log in, fire up a simulation to test their code, and within minutes they receive an angry email from the sysadmin. The login node went unresponsive. Everyone else who was logged in lost their session. This is the most common and most disruptive mistake in HPC. And it happens because most people enter a cluster without understanding the architecture they are working inside. Today I am changing that. You will understand what login nodes and compute nodes are, why they exist, how a job scheduler bridges them, and how the entire cluster is structured to run thousands of jobs simultaneously. What an HPC cluster is. A high-performance computing cluster is a collection of interconnected computers, called nodes, that work together to run computationally intensive workloads that a single machine could never handle in a practical time frame. A standard workstation has a limited number of CPU cores, a fixed amount of memory, and fixed storage. Scientific simulation, genomic sequencing, climate modeling, and large-scale machine learning training all require more compute resources than any single machine can realistically provide. An HPC cluster solves this by connecting many nodes together through a high-speed network. Each node is a physical server with its own CPUs, memory, and sometimes GPU accelerators. All of these nodes are managed together as a unified computing resource that users access through a shared interface. The most important thing to understand about an HPC cluster is that not all nodes serve the same function. A well-designed cluster assigns different types of work to different types of nodes, each optimized for its specific role. This separation is deliberate architectural engineering, not arbitrary convention. It makes the cluster stable, secure, efficient, and fair for all users simultaneously. Modern HPC clusters follow a standardized architectural pattern that you will find at universities, national laboratories, government research institutions, and cloud HPC providers, including AWS, Parallel Cluster, Google Cloud HPC Toolkit, and Azure Cycle Cloud. Once you understand this architecture from first principles, you can navigate any HPC environment because the fundamental structure is consistent across all of them. Let us build that understanding node type by node type. Login nodes, what they are, rules, and the common mistake. The login node is the entry point to an HPC cluster. When you connect to a cluster using SSH from your laptop or workstation, you land on the login node. This is the machine that handles user authentication, file transfers, source code editing, compilation, and job submission to the scheduler. The login node is a shared resource. It is used simultaneously by every user currently connected to the cluster. That is the single most important fact about login nodes. And it is the fact most beginners forget within their first hour. Because the login node is shared, it operates under strict usage conventions. Editing files, writing job scripts, compiling source code, and submitting jobs through the scheduler are all appropriate activities on a login node. Running actual computations, launching simulations, training models, or executing any process that consumes significant CPU, time, or memory is a violation of cluster etiquette and, in most institutions, a violation of the acceptable use policy. When a user runs a heavy computation directly on the login node, they consume shared resources that affect every other user simultaneously. If the process consumes enough CPU or memory, the login node becomes unresponsive. Sessions drop. Work is lost. At most institutions, this will result in the process being killed automatically and the user receiving a formal warning from the system administrator. Think of the login node as the reception area of a large research building. You pass through it to get where you are going. You check your email, drop off files, and submit paperwork. You do not set up a laboratory bench in the reception area and run experiments there. The same principle applies here. Compute nodes, architecture, types, allocation. Compute nodes are where actual scientific and engineering computation happens. Unlike the login node, which is interactively shared by many users, a compute node is allocated exclusively to a specific job for the entire duration of that job's execution. No other user's workload runs on that node until your job completes and the node is released back to the available pool. Compute nodes in a cluster vary significantly based on the cluster's intended workloads. Standard CPU compute nodes are the most common type. Each node typically has 2 high core count server processors, a large amount of RAM, and fast local temporary storage. A modern CPU compute node might provide 64 to 128 cores and 1 to 4 terabytes of RAM, depending on its configuration. GPU compute nodes are equipped with high-performance GPU accelerators alongside standard CPUs. These nodes are used for machine learning training, molecular dynamics simulation, computational fluid dynamics, and any workload that can be parallelized across thousands of GPU cores. Each GPU node typically houses 4 to 8 accelerators alongside the standard CPU configuration. High memory nodes, sometimes called fat nodes, contain significantly more RAM than standard compute nodes, sometimes 8 terabytes or more. These are designed for workloads with very large in-memory datasets that cannot practically be distributed across multiple nodes, such as large-scale graph analytics or whole genome assembly. The heterogeneity of compute node types within a single cluster is intentional. It allows the scheduler to match each user job to the specific hardware configuration that the workload actually requires, rather than allocating generic resources that may be over-provisioned for some jobs and under-provisioned for others. Here is something that surprises engineers coming from cloud computing backgrounds. In a cloud environment, you provision a virtual machine and interact with it directly. You SSH into your instance and run your workload on that machine. In HPC, that pattern does not apply. You almost never run computations by directly connecting to a compute node. You submit a job description to the scheduler, and the scheduler decides when and where to execute it on your behalf. You do not choose the specific node. You do not connect to it while the job is running in most cases. You specify what resources you need, and the system handles the allocation transparently. This is a fundamental shift in how you think about computing, and it changes how you write scripts, how you structure your workflows, and how you debug problems when something fails. The job scheduler, SLUM, the bridge between login and compute. The job scheduler is the software layer that sits between the login nodes and the compute nodes. It manages the allocation of compute resources to user jobs, enforces priority and fairness policies, tracks resource utilization across the cluster, and ensures that compute capacity is being used efficiently. SLUM, which stands for Simple Linux Utility for Resource Management, is the most widely deployed job scheduler in HPC environments worldwide today. If you work with a university cluster, a national computing facility, or a cloud HPC platform, there is a very high probability that it runs SLUM. PBS Professional and its open source variant OpenPBS are also deployed at many institutions, particularly in older environments. A user interacts with the scheduler by writing a job script. A job script is a text file that specifies 3 categories of information. First, the resource requirements for the job, meaning the number of nodes, cores, memory, GPUs if needed, and the maximum wall clock time the job is permitted to run. Second, the commands to execute once the allocation is granted. Third, any environment setup required for the application to run correctly, including module loads and environment variable configuration. The scheduler receives the submitted script, assigns it a job ID, and places it in the queue. It evaluates the queue continuously using priority algorithms that consider job wait time, requested resource size, and the user's recent usage history. When the requested resources become available, the scheduler allocates the appropriate compute nodes exclusively to the job and initiates execution. If you are building practical HPC skills for research or engineering work, subscribe and turn on notifications. Performance Engineering Academy is systematically covering every layer of the computing stack, from hardware architecture to workload management. This series is designed to take you from zero HPC knowledge to being able to use any major cluster environment with confidence. Now let us look at the other node types in a production cluster and walk through a complete job lifecycle end-to-end. Other node types: management, storage, visualization. A production HPC cluster contains more than just login nodes and compute nodes. Understanding the other node types completes the architectural picture. The management node, sometimes called the head node, runs the cluster's administrative services. It hosts the SLUM daemon, the monitoring infrastructure, the user management tools, and the configuration management system that keeps all other nodes in sync. Users never connect to the management node directly. It operates as the cluster's control plane, running continuously behind the scenes to keep the entire system functioning. Storage nodes provide the shared parallel file system that all other nodes mount and access simultaneously. This is architecturally critical. When a job runs across 100 compute nodes, Those nodes need a common place to read input data and write output results. Each compute node cannot store its own copy of the working dataset. The shared file system provides a high-throughput storage layer that all nodes can access concurrently. The most common parallel file system technologies used in HPC are Lustre and IBM Spectrum Scale, formerly known as GPFS. These systems are specifically designed to handle the I/O patterns generated by parallel applications running across hundreds of nodes. The shared file system is also a frequent performance bottleneck. When thousands of cores attempt to read or write small files simultaneously, the metadata operations on the file system become saturated before the actual storage bandwidth is exhausted. Writing many small files from a parallel job is one of the most common I/O performance problems in HPC, and understanding why requires understanding how the shared file system works. Some large clusters also include dedicated data transfer nodes, which are optimized for moving large datasets in and out of the cluster over wide area networks without consuming login node bandwidth, and visualization nodes for interactive rendering of simulation output data. The job life cycle, end to end. Now let me trace a complete HPC job from submission to completion, connecting all of the components we have covered into a single coherent workflow. A researcher on the login node writes a Slurm job script requesting 8 CPU cores, 64 gigabytes of RAM, 2 GPU accelerators, and a maximum wall clock time of 12 hours. The script loads the required software modules and calls the main application executable. The researcher submits the script using the spatch command. Slurm receives the submission, assigns it a job ID, and places it in the relevant partition queue. The scheduler evaluates the queue against the current state of available compute nodes. If the requested resources are not immediately available, the job waits. When compute nodes with the required configuration become free, Slurm allocates them exclusively to this job. The selected nodes receive the job's execution instructions from the scheduler. The application begins executing on those nodes. During execution, the application reads its input data from the shared file system, performs its computation using the allocated CPS and GPS, and writes intermediate and final results back to the shared file system. If the workload is a parallel MPI application running across multiple nodes, the processes on different nodes communicate with each other through the high-speed interconnect. When the application finishes or the wall clock time limit is reached, the compute nodes are released back to the scheduler's available pool. Slurm writes the standard output and error logs from the job execution to files in the user's submission directory. The researcher returns to the login node, examines the output files in their project directory, checks the error log for any diagnostic messages, and prepares the next job submission based on the results. Network interconnect, InfiniBand, MPI, and why it matters. The network connecting all nodes in an HPC cluster is not standard Ethernet. It is a specialized high-performance interconnect designed for the latency and bandwidth demands of parallel scientific applications. InfiniBand is the dominant interconnect technology in production HPC environments. Modern HDR InfiniBand operates at 200 gigabits per second per port, and the end-to-end latency between two nodes is measured in single-digit microseconds. This compares to the tens of microseconds typical of even high-quality data center Ethernet. The reason low latency matters in HPC is MPI, the message passing interface. MPI is the standard communication library used by parallel applications that need to distribute work across multiple nodes. When a simulation running on 1000 cores needs to exchange boundary data between processes on different nodes, it uses MPI to transmit those messages across the interconnect. If each of those messages incurs even a few extra microseconds of latency, and if they happen millions of times per second during a tightly coupled simulation, the accumulated overhead becomes the dominant factor in the application's runtime. The interconnect topology determines how bandwidth is shared across the cluster. A fat tree topology provides non-blocking bandwidth between any pair of nodes simultaneously, which is optimal for communication-intensive workloads. A dragonfly topology reduces cabling complexity at very large scale, but introduces some performance variability when traffic patterns are irregular. Understanding the interconnect architecture of your cluster becomes important when you are scaling an application across more than one node and find that adding more nodes improves performance less than expected. The communication overhead across nodes relative to the computation being done is one of the central scalability constraints in parallel HPC applications. Real-world examples: university, national lab, cloud HPC. Let me ground all of this in real cluster environments you are likely to encounter. A typical university research computing cluster might have 2 to 4 login nodes, one management node, 100 to 500 standard CPU compute nodes, 20 to 50 GPU nodes, a high-speed InfiniBand fabric, and a Lustre parallel file system. It runs Slurm as its job scheduler. Users from computational biology, material science, atmospheric modeling, and machine learning all share the same infrastructure, with queue policies set to balance fairness across research groups. National computing facilities operate at a much larger scale. The Frontier supercomputer at Oak Ridge National Laboratory contains over 9,000 compute nodes. Each node has a single AMD EPYC processor paired with 4 AMD Instinct GPU accelerators. The system uses HPE Slingshot as its high-performance interconnect. At this scale, the architectural separation between login nodes, compute nodes, storage nodes, and the management layer is maintained with exactly the same principles as a small university cluster, scaled up by a factor of hundreds. Cloud HPC platforms like AWS Parallel Cluster, Google Cloud HPC Toolkit, and Azure Cycle Cloud replicate this entire architecture in a cloud environment. When you deploy a cloud HPC cluster, you define a head node, a compute fleet, a shared file system, and a job scheduler. The default scheduler on all three platforms is Slurm. The skills and concepts from this video transfer directly to any of those environments. The architectural pattern is consistent because it solves a real problem universally. Any environment that needs to share large-scale compute resources fairly, efficiently, and stably among multiple users will arrive at some version of this same design. Let us bring it all together. An HPC cluster is a collection of specialized nodes connected by a high-speed network and managed by a job scheduler. Not all nodes are the same, and treating them as if they are is the most common mistake for engineers new to HPC. Login nodes are the shared entry point for all users. You use them for file management, code editing, compilation, and job submission. You never run heavy computations there. Compute nodes are allocated exclusively to user jobs by the scheduler. They come in standard CPU, GPU, and high memory variants matched to different workload types. The job scheduler, most commonly Slurm, is the bridge between login nodes and compute resources. It manages the queue, the allocation, and the complete life cycle of every job in the system. Storage nodes provide the shared parallel file system that all nodes read and write during job execution. The shared file system is both the backbone of the cluster and a frequent performance bottleneck. The high-speed interconnect, typically InfiniBand, enables the low-latency MPI communication that parallel applications depend on. In the next video, I'm going deep into Slurm job scripting from the ground up, including how to write efficient job scripts, request resources correctly, use job arrays, and diagnose the most common job failure modes. If this gave you value, like the video, share it with a colleague who is new to HPC, and subscribe to the channel. Drop a comment with the job scheduler your institution or organization runs. See you in the next one.